like at t equals 0, because we always have to have that information. And for an inductor, you'll be looking at current. For capacitors, you'll be looking at voltage. And so before t equals 0, actually, let's take a look, since all it says is find IL of t. Let's take a look at what we would need to have for IL of t for an inductor. What we're going to need to have is we're going to need to have I of 0, I at infinity, and the time constant. In order to get I at 0, you have to look at before any switch action. The same is true for a capacitor. To find the voltage for a capacitor, you have to look before switch action. Because right when the switch changes, this whole circuit may change, but whatever current you had through the inductor can't change instantaneously. So even if you look at it, you think, oh, well, it has to have a current because it's connected. If it didn't have a current before, it's not going to have a current right after. And so for I equals 0, you have to look at before any switch action. That's for an inductor. If it was a capacitor, that would be for voltage. That's what you'd have to do. So before the switch, the inductor is an open circuit. It's not a complete circuit. So before t equals 0, what a lot of books call 0 minus, IL of 0 minus is 0. There's no current flowing through it. And since it can't change instantaneously, we know IL of 0 is also 0 amps. Okay, so now let's go ahead and draw what the circuit looks like right after the switch. Okay, so there we have right after the switch. And we'll come back to that when we need to figure out what the time constant is. And now let's look at t equals infinity. So at t equals infinity, what is the inductor going to do? What does an inductor do after a long time? It acts like a wire. Okay, so whenever we are looking for the voltage across the capacitor, we find something the capacitor is in parallel with. If we want to find the current through an inductor, what should we look for? something it's in series with. Now, also, let's take a look at this circuit that we just drew. When that inductor becomes a wire, what does that do to the 25 ohm resistor? It shorts it out. Anytime you have a wire in parallel with the resistor is going to be shorted out. So we can rewrite this like this. Whoops, not like that. Like this. Okay, so now we've got this circuit, and our job is to find this current right there. That's IL. So let's do some nodal analysis. Okay, so let's start at VA. So for VA, for nodal analysis, current sources coming in are negative, current sources going out are positive. So that 1 amp will be negative. We know that actually, I'm going to not write it. I'm going to change this up a bit. And I'll explain why in a minute. I'm going to put my ground right here. And you'll see why in a second. You'll see why in a second. Put my ground right there. Okay, so, and this is VA. This is VB. Vx was labeled as the voltage across this this resistor right here. So well, actually, I think I like it better the first way, because it's not Vx if I put the ground over here. Because if I put the ground, so I'm going to go back and put the ground where I had it the first time. So then I will make it Vx. So. Okay, so let me explain what we were just talking about right there. So if the voltage across this is Vx, and I'm labeling these things relative to ground, if this is ground, then this is Vx right here. Because the voltage change across this is 0, the voltage change across this is Vx, so this is Vx up here. If I had put ground over here, then it wouldn't be 0 on the bottom anymore. 0 would have been over here on the other side of the resistor. I was originally going to do that because of this dependent voltage source, and then I decided I didn't like that after all. Okay, so I said that currents coming in are negative, so that's -1, and currents going out are positive, so this is the current coming out is plus IL going in this direction, because these are all in series. And it also has a current going down of Vx over 10. And all that has to equal 0. And then I also know that Vx minus 0 over 5 has to equal IL. How do I know that? This current right here. Oh, no, but I have this 0.4 volts, and so, sorry, we would need this, it's not going to be Vx. Yeah, it'd be VB right here, VB, sorry. This should have been VB. VB. VB minus 0 over 5 equals IL. Now, what do we know about VA and VB? What is VA minus VB?
Vx minus VB is 0.4 Vx?
Yeah, or Vx minus VB is 0.4 Vx, because the label on a voltage source is always the voltage on the positive side minus the voltage on the negative side. So we have Vx minus VB equals 0.4 Vx, or 0.6 Vx equals VB.
Excuse me.
Yep.
For VA, you have like VA A1 plus IO. Like what? Tell us what's that?
Nodal analysis.
Why do you have IL?
Because that's the only way for me to get the current going out on this side right now. So nodal analysis, what it is all the currents coming out.
Right.
And at this point, I don't have a better way of saying what that current going out is. We're about to do some substitution and put other stuff in. Right now, I'm just saying, right now I'm calling it IL because I've got that freaking dependent voltage source right there.
Okay.
Does that make sense?
Yeah.
Yeah, okay. So generally what you do with nodal analysis is, if you're lucky, you have nice resistors on every side, and you know exactly what the voltage is on every end. And you would say VA minus, or this is V1, V2, V3, VA minus V1 over R1 plus VA minus V2 over R2 plus VA minus V3 over R3 equals 0. Sometimes you also have a current source. And so when you have that current source, then you just use the currents. So if that's I1 and that's I2, and I have V1 over there, it'd be V1 minus, or V minus V1 over R minus I1 plus I2 equals 0. In this case, I just had a big mess over here because of this dependent voltage source. And so I said, to start off with, I'm just going to call it IL and we'll figure it out later. And that's where we are. That's the step we're at right now. So we have some various equations. We have that VB equals 0.6 Vx. We have that VB over 5 equals IL. And this is what we're going to use. And we have that minus 1 plus IL plus Vx over 10 equals 0. So now I can substitute in, let's see, so VB over 5 equals IL, so VB equals 5IL. VB also equals 0.6 VX. And so 5IL equals 0.6 VX, or VX equals 5 over 0.6 IL. Can someone do 5 divided by 0.6 for me? So minus 1 plus IL plus 8.33 IL over 10 equals 0. And then we could get what IL was. And if anybody solves for IL, if you could tell me what it is. 4 point.
Oh, no, I'm sorry.
That was that the 8.33. No, so that this is negative 1 plus IL plus 0.833 IL equals 0. 1.833 IL equals 1, or IL equals 1 over 1.833.
0.545.
Yeah, I got distracted myself.
Oh, okay. Well, see if your Vx gives us a 0.545 amps.
Yeah.
Okay, so all of that gave us 5.545 amps equals V at infinity. What else do we need to know in order to write the equation for the current at any time t? We know I at infinity now. We know I at 0.
Oh, we need to do the tau.
We need to do tau. What do we need to get for tau? We need the equivalent resistance.
I forgot how to do it with the
Yep. So we want to find the Thevenin equivalent of this circuit at t equals infinity. We need to find R equivalent. So and how do you do that with a dependent source? One way to do it is V open circuit over I short circuit. Luckily, we know what I short circuit is, don't we? Isn't that exactly what we just solved for? Yeah. So, so this is how you find R Thevenin for if you have a dependent source. It's V open circuit over I short circuit. We already have I short circuit, so we just need to get V open circuit. All right, so we need to find V open circuit. And when I did this in the session, I used this circuit right here, which is the circuit at infinity. But during the transient, this 25 ohm resistor has not been shorted out yet. So we have to include that when we are finding V open circuit. So for V open circuit, we would have this. And we need to find the voltage across where the inductor would be. So it's still going to be true that if we make this ground right here, I forgot my 5 ohm resistor. If we make this ground right here, then if we have 0 here, then we have to have 10 volts right there because of our 1 amp voltage source. And so we know that we have 1 amp here, and no, we don't know that anymore now that we have that other branch. So let me erase that. That might not be 10 volts. Okay, so let's do, I like voltage nodal analysis, so I'll put V1 there, and then that's the same as Vx, and this was 0.4 Vx, and as I said before, if that's 0.4 Vx, then this side has to be 0.6 Vx, because what this means, and when you have the label and a voltage source, it means the voltage on the positive side minus the voltage on the negative side equals the label on the voltage source. And so we know that 0.4 Vx. We know that on one side we have Vx. On the other side we have, I'll just call it V, and the difference there has to be 0.4 Vx. And if you solve for that, you get that V is 0.6 Vx. Okay, so the voltage right there is 0.6 Vx. So from Vx, our node equation would be negative 1 amp plus Vx over 10, and then going to the right, so let's look at what's happening going to the right. We're going to have, we'll have a current here, and whatever current we have here, that current has to also go through this branch because it doesn't have anywhere else to go. And so the current through that branch is going to be 0.6 Vx over, this was 25 over 30, because this current has to go all the way through there, and that current has to be the same as the current coming through there. So that gets us all we need. And now if I multiply through by 30, I get negative 30 plus 3 Vx plus 0.6 Vx equals 0, or 3.6 Vx equals 30, or Vx equals, do I not have a calculator open? I don't. So 30 divided by 3.6. 8.33. So Vx is 8.33, but we want the voltage across the voltage source, across the inductor, which is right here, which will be the same as the voltage across the 25 ohm resistor. So remember, this was 0.4 Vx, and the voltage on this side was 0.6 Vx. And then we had this 25 ohm resistor, and then we've got our inductor right there. So let's get 0.6 of Vx. And that gives us 5. Okay, so our voltage right here is 5. This was 25. And so, and this is not 0 down here because there's also a 5 ohm resistor right there, and ground is right there. And so our voltage, this was 5, our voltage across the 25 ohm resistor will be by voltage division, 5 times 25 over 30. Which is 4.167. And that is V open circuit. And so to find R Thevenin, we need V open circuit over I short circuit, and V open circuit is 4.167, and I short circuit we found was 0.545. And so R Thevenin is 7.64, and tau is L over R. L was 5 over 7.64. .654, and then 1 over tau is 1.53, and so that gets us I at any time t equals I at infinity plus I at 0 minus I at infinity e to the minus t times 1 over tau. So that would be 0 plus 0 minus 0.5454 e to the negative 1 over tau, e to the negative 1.53 t, or negative 0.5454 e to the negative 1.53 t amps is I of t.